Yes? Good. Maybe. Okay. It's actually a beautiful marriage between Physics 1 junior and Physics senior level. What's the difference between junior physics and senior physics? Calculus based. Okay, so if junior physics is not calc based, then what is it? Algebra based. So you cannot tell me how fast something is going at an instant in junior year? That's correct. All you can say is how fast something is going over an interval. That said, say you went 50 miles over the course of 1 hour. Your average rate is
50 miles an
50 miles per hour. That's not a trick question. Does that mean that every instant in the interval you are going 50 miles per hour?
No.
No. Was there an instant where you must have been going 50 miles per hour?
Yes.
Yes, that's the case of the mean value theorem. Okay? The big idea of the mean value theorem in plain old English is under certain conditions, average rate of change, or if you like, secant slope, if we look visually, equals instantaneous rate of change, or tangent slope, if I look visually. Okay? The conditions, though, are in the formal mean value theorem as written for you in that box. If f is continuous, now this is where you get really fine points here. F is continuous on the closed interval a to b. It's got to be continuous up to and including the endpoints. And differentiable on the open interval. It does not have to be differentiable at the endpoints. Then there is a value in the interval, in the interior of the interval, where and this is where the star of the show is, the instantaneous rate of change equals the average rate of change. Now, if you think about it, it's pretty clear why it has to be continuous up to and including the endpoints, because it's kind of hard to calculate this if the function doesn't include those endpoints. Yeah? So, why closed interval? Well, f at a and f at b have to be there for this whole idea to work. The differentiable, well, that also kind of makes sense. If this idea is going to work, then the derivative has got to exist, right? So the conditions are necessary in one way. Let's draw a picture to show the big idea. Consider this curve. Would you draw a nice cube like this? This endpoint that is included is A. This endpoint, which is included, is B. Okay? The idea of the mean value theorem is if you look at the average rate of change between the endpoints, that's the slope connecting the 2 points. Well, why is changing big and small and stuff? The total average rate of change over the interval would be that, yeah? There's got to be a place where the tangent slope, so that's secant slope right there, secant slope. There's got to be a place where the tangent slope is like that slope, or same rate of change. In this case, there are actually 2. Notice it says at least one value. Not exactly one value, at least one value, where the instantaneous rate of change equals the average rate of change. All right, let's also draw a doodle or two to show why continuity is necessary. Say you had the old, let's do a vertical or a vertical asymptote / infinite discontinuity. Say you had 1 over x. And you were talking about on the interval -1 to 1. Okay? It's got a closed interval. It's all good. It's differentiable at a lot of places. The average rate of change, here's -1 and here's 1. The average rate of change is what? You are really killing me. You're trying to kill me right now. What is the average rate of change? The slope, please. 1. Thank you. Oh, you're just shy. The average rate of change is 1. And yet, if I try to draw a place where the tangent slope is 1, these slopes all negative. These slopes all negative. There is no place where the instantaneous rate of change equals 1. And that's why then continuity is essential. It kind of makes this huge jump in y values that throw the whole thing off. Why differentiability is necessary. Say you did the same kind of endpoints as the cube over there. Say you had 1 and then 1 a little higher enough to the right. All right? Now I know that the average rate of change would be that slope. But imagine if in between the curve did something like this. Whoop, whoop. Try and draw a place where the instantaneous rate of change or the tangent slope looks like that. These are all negative-ish, and then it just goes straight to a steep positives. Is there any place where the tangent slope's like that? No, because the slopes went so straight from steep negative to steep positive without hitting all the slopes in between, smooth transition slope, you could say because the derivative isn't locally linear, that the whole thing is up, right? So those are the conditions. Now let me get a few book problems, and then we'll get to a few AP-ish kind of problems, and we'll practice this a lot tomorrow as well. The book problems will look something like this. Given f is the square root of x, must there be a place in 0 to 4 such that the derivative is 1/2? Now students want to just say, find the derivative, show it equals 1/2. Yeah. That's not really the intention of the question, to show, hey, here's a derivative equal 1/2. See, there you go. The idea is prove it by NBT. This is what I would like to see. First, is f continuous on the closed interval? Is it continuous all the way up to and including 0 to 4? Yes. Write that. You may abbreviate. You may even say f continuous on, but I need you to write that each time, partially because the more you write it, the more you remember it. Is f differentiable on the open interval? Okay, now you're just, at this point, just saying yes, because I know you didn't take the time to think about that. What's the derivative? 1 over 2 root x. Does that derivative exist on 0 to 4?
Yes.
It exists on the open interval 0 to 4, because does it exist at 0? It does not. All right, now that's okay, because the mean value theorem, that C at which you draw, the C is the point at which you're finding the instantaneous, it's always on the interior. Okay? So the fact that the derivative doesn't exist at the edges isn't a problem, because the place where I'm going to find that derivative is in the interior anyway, so it's okay, it's okay. Here I go then. By NBT, I met the conditions. Now I start saying, all right, here's my reasoning. By NBT. You may abbreviate NBT in my class and on the AP test. It is acceptable. It's no problem. There is a C in 0 to 4. This, by the way, should have been an open interval 0 to 4. C is in the open interval. It's not at the edges. That's a typo I forgot to change. Such that, or where, whichever you prefer, such that, and here's where we start writing the old theorem. F prime at C equals F at 4 minus F at 0 over 4 minus 0. Now that's the MBT, but so far I don't have anything about the half in there. Well, that's going to come from the average rate of change. The average rate of change on the interval is, what's F at 4? 2. What's F at 0? Over 4 minus 0. So the average rate of change is a half. It's meeting this average rate of change condition. So there's got to be a place where the derivative is 1/2. So, boom, I answered the first part of the question. Yeah, there's got to be a place by MBT. Unfortunately, they also said, all right, now find it. Well, how do I find it? Yeah, let's work besides the right side, which the right side's pretty much done. The derivative, the rate of change on the average rate of change is 1/2. How do I work the derivative part? Set it equal. Yeah, 1 over 2 root c, really, not x. Because it's f prime at c written there, I should be talking f prime at c with a c in there. 1/2, and I solve. What c would make that true? C of 1. Okay, is that in the interval 0 to 4? Yeah. Visually, we found that the average rate of change is here, and the place where the instantaneous rate of change is the same. My picture is not to scale. All right. Try one on your own, get a little practice, and then we'll move on to the more common types on the AP test anyway. This is how Saxon out from words and height. I'd love to ask him, does that mean that you're saying the MBT is applicable and I don't have to meet the conditions? I don't know. So I just am in the habit of meeting the conditions on my own anyway. And that's what I'd like you to do. Well, x isn't necessarily continuous and differentiable. Are we okay here, or does it not even apply? On that interval it is, yes. So if they had gone negative 1 to 4, we would have been some. Maybe I should just work this down instead, shall I? Hi.
Hello.
Thank you. Negative 1 over c squared equals negative 1/4. Seems like that indicates c is plus or minus 2. Yes? No. Only 2, because the interval does not contain negative 2. Negative 2 is not 1 to 4. So c equals 2 is the number guaranteed as by the MBT. Sorry. All right. Now these are more fun. The table here. Truth be told, the real use of MBT is that in real life you don't get handed, hey, here's an equation, work it. That's not how it works in real life. You get data. And if you want to make an equation, you need to make it yourself, making a mathematical model. Getting numerical data is far more common. So you want to be able to use your calculus. Well, MBT is how you take that, here's your data of numbers, average rates of change, and being able to say there is derivative equal to this and that. It's the bridge between average and instantaneous. So this is we're going to start off easy and gradually get harder. Okay? So you've got a twice differentiable function. Please note that that's for all tables. All the tables below, they're all twice differentiable. Okay, I didn't say it every time, but every table from here on out, they're twice differentiable. Does differentiability imply continuity? Yes. Okay. Is there a place in 0 to 2 such that the derivative at that point must be 1? Well, what the heck? I don't even have f prime, but I do note that the average rate of change is 2 over 2, so the average rate of change is 1. So must there be a place where the instantaneous rate of change is 1. Well, that's the MVT idea. Okay, so wording it, we would say something like F is continuous and differentiable. Although the AP probably wouldn't require you to cite why you say that. If you wanted to, you could say because F is twice differentiable. It's given. That would be optional. But you do have to say that the conditions, you know the conditions and they're met. Also on the AP test, in terms of the free response, they're not super picky about the endpoints, open interval, closed interval. F is continuous and differentiable, so by MVT, cite the theorem. There is a, and you name it, let's call it, they actually named it. They said to call it C, so I need to call it C. There is a C in 0 to 2, such that F prime at C equals F at 2 minus F at 0 over 2 minus 0. You've got to show that. Do not go straight to the table. You've got to show where you're coming from. After you said that, then go to the table. 7 minus 5 over 2 minus 0 is. There's got to be a place where the instantaneous rate of change is 1. You try. I think it's on the back. Different table, by the way. You get something like that. Yes? No? Okay. Let's gradually get a little rougher. Say you have that same table, working from the same table. Must there be a C in 0 to 8 where the derivative is 0? Well, look at 0 to 8. That rate of change is not 0, so do I say no?
Average rate from 0 to 3 is 0.
Ah, yeah. So you don't necessarily, now this kind of idea where they don't give you the AP test doesn't usually mess with you that much. They're pretty much happy if you can just have a clue on the MVT. And so they'll give you softies where you use the interval, and it's just like you just kind of use their endpoints. However, I would like that you are able to think and adapt, as Quentin just said. You can see that while 0 to 8, the average rate of change isn't 0. From 0 to 3, the average rate of change most definitely is 0. Anywhere else? Yeah, from 7a, you could also say similarly, that average rate of change is 0. So there should be 2 times? At least 2 times. Never read too much into the table, okay? You don't know what's going on in between. So there's at least 2 times. Now, they don't say how many times. They just say, does there have to be a time? So really, we only need to find 1 to satisfy that question, okay? So let's start with this. F is continuous and differentiable. So by MVT, let's say this in an intelligent, clearly communicated way. There is a C in, now I could say it's 0 to 8, but let's do better than that. Let's show when it happens. So in 0 to 3, and as he did, I like that point and clarified that. And therefore, in 0 to 8, such that f prime at c equals f at 3 minus f at 0 over 3 minus 0. You can see why it's kind of necessary to say 0 to 3 rather than 0 to 8, because if you say 0 to 8 here, but down here you're going 0 to 3, it's kind of this crazy, what's he doing kind of thing, all right? So, that. If you really wanted to overachieve, you could say similarly there must be a second point in 7 and 8. Now this actually is a subset of mean value theorem, a special case of mean value theorem. If you see places where the y values are the same, then that implies that the average rate of change over that interval must have been 0. Now, so what? So what if you see two places where the y values are the same? Well, if the average rate of change is 0, then there must be a place in between where the instantaneous rate of change is 0. And that's a pretty darn good candidate for a min or a max or both. Okay, so you can see why Rolle's theorem might be important. If f at b equals f at a, that implies that f at b minus f at a is 0. There's no difference between the y values, and therefore the average rate of change must be 0. And by MVT, that would imply that the derivative must be 0. That's Rolle's theorem. So if I say Rolle, it's saying MVT, but the specific case where the average rate of change is nothing. You follow? Okay, let's work harder now. I just told you can find Rolle cases by saying, well, if the y values are the same, boom, average rate of change 0, derivative 0. So what about this example 4? Is there a place where the derivative is 0? I don't see any y values the same, so I conclude no. Or do I conclude no? Do you conclude no?
No.
No, you don't. You think more. Think about it, and I will tell you, or we'll talk about it later. Try it on your own, or with the mathematical. Must there be a place where the derivative is 0? Even though I don't see two similar y values. If you're visual, sometimes it helps to make a quick doodle.
It has to be negative from 0 to 2 at some point, positive. Because the derivative slowly changes.
You understand the concept, and it's how you think. That's the hard part for me, right? So those of you who are thinking about how to write this up, let's talk about it maybe together. Do you agree? Why? Let's just start big idea. Why must there be a place for the derivative is 0?
Because somewhere between 2 and 3.
They're decreasing. They're decreasing, so that implies that the derivative must be negative the whole time, or at least once. Okay, so the derivative's got to be negative in here, and then the function's increasing, so the derivative's got to be positive somewhere. Can the derivative go from negative to positive without being 0? Yeah, you got to know if f is differentiable. Does that imply that f prime is continuous? you're on a little bit of a slippery slope there. Okay? Key is not differentiable. Key is twice differentiable. Okay? If it's twice differentiable, then f prime is differentiable. I'll say, if it's twice differentiable, then the second derivative exists, right? That means I was able to take the derivative of f prime. Now, if I could take the derivative of f prime, that's only if f prime is differentiable and therefore continuous. And so we could go about this in a kind of MVT twice with IVT mixed in for a little spice in there. That's how we're going to do this, right? So f is continuous and differentiable. So by MVT, there is a. Now you can use lots of different letters. I use C, C1, C2, and so on. There is a C1 in. Where's my first interval I want to look? 0 to 2, such that. Now, you could say f prime is negative, but you really need some evidence in there. F prime at C1 is. Now, at that point, you could say is negative, but geez, you're almost there. You might as well just figure out what the heck it is. What is it? Negative 1/2. Now, really, all you really care about is that it's negative. But we'll make the calculation. Negative. So great. There's a place in here, there's C1 in here, where the derivative is negative. Great. Then what do I do? What's the next step in my writing? You establish f prime is negative. Now you need to establish f prime is positive. You don't have to meet the conditions again. You can just say, similarly, there is a C2 in what interval? Can I go 2 to 3? Sure. Can I go 2 to 4? Sure. Can I go 4 to 6? Sure. Whatever you want. Just as long as you show it's positive some other time. I'm just going to go 2 to 3 because it's adjacent. There's a C2 in 2 to 3 where, or such that, f prime at C2 is f at 3 minus f at 2 over 3 minus 2. What is that average rate of change in that interval? 3. Well, the derivative just went from negative 1/2 to 3. What must it do in between? Okay, by IVT. All right. So, let's say IVT well, which you usually do well. It's been a while, so let's review it. F is twice differentiable. So f prime is continuous. You can't use IVT on f prime unless you say f prime is continuous, right? And it is. Because f is twice differentiable, f prime is continuous. So by IVT, what? Now what do I do? There's what? Oh, yes, there is a C. I don't know how you guys say this, but I would say there is a C3 in where? 0 to 6 is true. I actually say C1 to C2, but I suppose 0 to 6 is true also. In, you could even say 0 to 3, really. There's a C3, and I just say it's between C1 and C2, where F, what, prime or F? F prime at C3 equals 0 because 0 is between negative 1/2 and 3. If you really wanted to overachieve, you could say f at C1, which is negative 1/2, that's f at C3 to be 0, then f at C2, which is 3. Two. Yeah.
What if you use IVT first to prove that there's some point between 2 and 3 where F is like C1 is equal to 2.
Oh,
So rather than doing NVT twice than IVT, you just do
Oh.
IVT and NVT once.
totally didn't see that. What a great idea. Did you follow that? Okay, so rather than MVT, MVT, IVT, could you, we just talked about how it's awesome when there's two Y values that are the same, because then MVT is 0, right? He's saying, could you, oh shoot, wrong way. Could you say, still wrong. Could you say there's got to be a place in, where, in here, where F is 2 by IVT? And then say,
I just did less work, so I'm
Yeah.
okay with
That's what I
that.
would say.
and then there's got to be an average rate of change of 0. And that's awesome. I love it. So you would say by IVT, there is a C1 in 2 of 3, where F at C1 is 2. And then you'd go with 0 and C1 for your MVT. Beautiful. Great idea. Okay. Try the hardest case. Now I'm anxious to see if there's an easier way to this. Try this. Second derivative. Must there be a place where the second derivative is 0 given that our table? There's definitely an easier way, a harder way to look at this.
Is it intentional? Is the table supposed to be bigger than the range?
Oh, no, this is supposed to be 0. Oh, shoot. Sorry, 0 to 9. Change that to 0 to 9. Sorry, this is supposed to be 0 to 9. My bad. Although it is 0 to 7 works too. 2 to 4. Say it again.
Why is it 6?
It's 2. Silly goose.
It's like if you're going from 2 to 3,
Okay. So just so you don't go in the hard way, it's very common to say, all right, there's got to be a place where the derivative is 1, derivative is -1, derivative is -10, derivative is positive 10, derivative 2. And then say based on those, the second derivative or change in those would have to be -2, -9 at some point, 20 at some point. And then say, oh, see, second derivative went negative to positive, boom. Now that's going to stink because you've got to do an MVT here, 2 MVTs, 2 MVTs, and then another MVT with IVT. So 5 MVTs and 1 IVT after that. What's a better way besides looking at change from one point to another?
Use FVT 3 times to find, to prove that F prime is 0 between 0 and 5, but do it again between 5 and 8.
Yeah.
And then use FVT to prove that prime is 0 between those two, because the average between those two is here.
It's always easiest to look for places where the y's are the same. Okay, so you should, rather than go point to point, look at how 0 to 5 is working and 5 to 8, like you said. if the derivative has to be 0 and 0 to 5, and the derivative has to be 0 and 5 to 8, then the derivative is going from 0 at one point to 0 at another. Doesn't then the second derivative have to be 0 somewhere in between?
It's like a median line.
Uh,
The median, you have to line compute if it goes above the line for one line, and then if it goes below the line for another line. So that means that there has to be an inflection point continuous and
what theorem are you using there? I've never heard of that.
oh no, I just kind of thought of
I understand what you're saying, and conceptually speaking, I would agree, but to prove it would be more work. Yeah. Yes? Where did I get these? I looked at the average. Oh, so actually, you're right. You're saying they're wrong because I'm looking at the y values only. Is that what you're saying? Yeah. It's actually not super duper critical, as the sign would be the same, but you're right. F prime wouldn't actually be 1 here. It would be really 1/3 and negative 1/2 and negative 10 seconds or 10 firsts or 2 or you're right. I was taking great liberty. They're not going that way anyway, so it doesn't matter. Okay. I would say find a C1 where the derivative is 0, find a C2 where the derivative is 0, and then use MVT at a second level. Let you try to write that up well, and we'll see how you put it out, and then we'll be
I'm so upset.
There's lots of places to make a mistake. Say F when you mean F prime, or say F prime when you mean F double. So be careful. Yes. Thank you. Okay, so I found 2 places where the derivative has to be 0. I call them C1 and C2, yeah? Well, if the derivative is 0 at one place and 0 later, then regardless of what the derivative did in between, doesn't there have to be a place where the slope of the derivative graph has to be 0, yeah? So let's say it here. Can I say similarly? No, this isn't really similarly anymore. I'm not talking about the same thing. So what now?
F prime is continuous and differentiable variable because F is twice differentiable.
Okay, yeah. I'm using MVT, applying it to F prime now instead of F. I'm saying the slope of F prime has to be 0, which says F double has to be 0. So you're using MVT at an F prime level. F prime is continuous and differentiable, and we say that, and we can say that because F is twice differentiable. So by MVT, as applied to F prime, there is a C 3, I suppose, in C1 to C2, such that, and here's where you're careful with your notation, F prime, F, or F double? F double where? At C3 equals F prime at C2 minus F prime at C1 over C2 minus C1, which must be 0. That's as ugly as you're going to see. Yes, ma'am?
Why couldn't you actually say F, and, or F prime and F double prime is continuous in those two? Or great?
I did have to say it at different points. Here I only had to say F is continuous and differentiable because I was only applying MVT to F itself. Down here I had to say F prime is continuous and differentiable because that's why I was applying it to F prime. So it kind of depends on what you're applying it to, that what you're saying is continuous. I guess you could kitchen sink it and say F and F prime.
But then I also don't know F double prime.
That's true. Good point.
So I couldn't do that.
True that. Okay, that's it. How about questions on, we'll do AP practice on that tomorrow. What about questions on 84? 84, question for me, if you have them. Easy? What? 3. 3. 3. All right. 14. Can somebody say another one?
15.
15. 1. One's a good one. One's a humdinger, all right. Okay, 3. Balls thrown horizontally from the top of a 100-meter tall building. This is actually a big part of Calc 2, by the way. Parametric equations and projectile motion in 2 dimensions, rectilinear movement. Thrown horizontally. Da-da-da. It is a fact that the height of the ball to given thrown has been dropped. Find the equation that describes the height as a function of t. So, is not height the antiderivative of velocity? And velocity is the antiderivative of acceleration. So if I anti-differentiate, is this meters? Negative 9.8 dt, then its velocity is negative 9.8 t plus a constant. If it's thrown horizontally at some rate, then its initial velocity, vertically speaking, is nothing. And so that implies that you are contributing nothing to the vertical velocity. Negative 9.8 t. The height then is the antiderivative of that, which is negative 4.9 t squared plus a new constant. And they say at time 0 the height is 100 meters. So that tells you that C2 is 100. Okay? After that, I don't know how long would it take to hit the ground. Ooh, so the third part is the good part. B, windshield grade hits the ground if h equals 0.
Yes.
And that's at negative 4.9 t squared equals 100. So t is the square root of 100 over 4.9, which I imagine is about 4 or 5 seconds. Okay, C then, we're going to need that for part C. If the horizontal velocity is 20 meters per second, what's the horizontal distance the ball will travel? The horizontal distance is how fast it travels horizontally times how much time it's in the air. Think of its rate times time, that's in essence. Okay? the rate horizontally is, you throw it horizontally at 20 meters per second. That whole thing is in the horizontal direction. It's in the air for 4 or 5 seconds, whatever that is. And so I would expect it to travel about 100-ish meters.
83.16.
Yeah, 83.16 meters before it hits the ground. Good one, good one. 14. Is 14 still a question? Come to me.
Yes, please.
Yes, 14. Replaced her straight up.
Replacement.
Oh, that's the cinch, yes. Okay, got it. 14. 0 to 1. This gets a little sloppy. Okay, did you use up? Now, here's where a little pointer for you, okay? Do you agree it's a big hassle to use up when there's limits?
Yeah.
Okay, so if it's clean, can you mental use sub? What's U here? 14. This says 14, Sully, don't you know?
I'm trying to question about when you
Oh, we're doing use of zeros caught 2x. Can you use sing cinch 2x dx?
Yeah. Now, here's where I would strongly recommend. I did this by use sub because I thought you folks would do it by use sub, but gosh, it's so much easier if you do it by mental use. Because then you don't have to change the limit. So, if U is cosh 2x, then du is cinch 2x times 2. What do you want there to be here in order for your U sub to go up? You want there to be a 2, which I can put there as long as I balance with the half. Now that then allows you to at least mentally picture the antiderivative of U to the 4th, which is 1/5 U to the 5th. But that was all in my mind, because on paper I kept it. I didn't actually use sub, I just kept it as cosh 2x from 0 to 1. You follow? So something like 1/10 cosh of 10 minus cosh of 0. And I suppose you could say, what is cosh of 10 is something, I don't know. I guess it would kind of depend if there are multiple choices. What's that?
where did the 10
These two.
so
Oh.
what's cosh
You mean, why isn't it?
2, right?
Yeah, so it should be 1 to the 5th minus cosh of 0 to the 5th. That's what you're saying. Is that what you're saying?
Why is it, how is it bound to 1 if it's 2x? What? It's 2 times.
Oh, now you're saying, why is it? Wow, I'm really having a rough time. Yes, cosh of 2. When you put in 1 and it's 2x, you get 2. Thank you. You're right.
I think you would not have to change the bounds of
Because I didn't actually change these to U, I kept it cosh the whole time. Okay, so because it was cosh, the limits can stay for cosh. If I actually use subbed it, gotta change the limits.
So I tried to do something and I looked at the key, I don't understand how you change the bound for the upper bound.
Okay? So if U is, oops, sorry.
Well, because on the, when you change it for the upper bound, it gives the caution. I don't understand why you use one for the caution.
Did I? Sure. If, I probably made a mistake then. If X is 1, then U should be cosh of 2. You're right. Did I use cosh or did I use E?
You did caution 1 and then you put it in the E form and
It's gonna tear it up.
2 and I don't understand why you put E to the 4.
Yeah, because I don't think Tyler probably has it.
If you went U form, that's what it should.
Yeah, but if you go caution 2x and you're putting in 1 Four.
I'm plugging in 2 into cosh of x is e to the x plus e to the negative x over 2. So cosh of 2 is e to the 2.
21. Wait. No, but cos of 2x equals e to the negative e to the 2x.
And x is 1.
With x, I already have 2 in there. If x is 1, then the fact that I'm using 2 means I'm doing 2x, right?
Oh.
Right? Oh,
Yeah, I see.
okay. So you could go that way. And then it would be something like this, if I remember right. That works. Okie dokie, that was hideous. Let me know if you want me to continue on anything.
25.
25?
Yes.
Okay, so as you might at least see now, they're trying to prep you for mean value theorem. They're saying you've got x cubed on negative 3 to 3, which is this steeply growing function, I imagine. Okay? And find the points where the line tangent to the curve. So tangent to the curve is parallel to the segment between the endpoints. Now that, we know today, is the mean value theorem. The tangent to the curve is f prime. At some point needs to equal the segment between the curves. That's the average rate of change between the endpoints. So that's the key, is the translation into calculus. Go there. Then you say 3x squared is something like 27 minus negative 27 over 6. 3x squared needs to equal 9, which means x squared has to equal 3, which means that could happen at plus or minus root 3. Because there are 2 places. The y values are plugging into points on the curve, so if it's x cubed, then root 3 cubed would be root 3 times root 3, yeah, x to the 3 to the 3 halves.
Oh, so it's not 3 to the 3. Can you not do that?
3 to the 3 halves is the same as 3 to the 3.
You just multiply it up with the fraction.
Yeah.
Oh, yeah.
3 to the 1 is 3, and 3 to the half is 3.5, so it's all good. Okay? Say, yes, sir. Sure.
I'm gonna have to come back for number 3.
Oh yeah, wait, just do 1, because after, please, because I don't know how.